Good morning, everyone. Again, sorry I'm not there today with you. Sorry I'm not teaching this. I do want to apologize also to sophomores or seniors who are having to listen to this for 2 days straight. But anyways, you hopefully got the lesson either today and you won't really have to focus tomorrow, or if you're watching this on Thursday, you got it yesterday, so you won't really have to focus today. But again, I expect that you stay calm and quiet so your classmates can pay close attention. Anyways, I left some of these blank because I wanted to talk through a couple of them. Some of them were so easy, I didn't really feel like it even merited that. But this was the homework from yesterday when we talked about theoretical probability. Anyways, as you can see, you were supposed to do the odds. I've given you number one. That one is about as easy as you can make it. And then number five as well, which is a different problem. It comes from the word candlestick. And there's only one N, there's only one S, so that's 2 out of 11. But I want to talk about number three before we move on. There's about 3 or 4 of them I'd like to discuss. This, of course, is a multiple of 5. But again, when I told you guys the other day, what I like to do is I like to find the bottom number first. Well, this is coming from the numbers 10 to 99. A lot of times what people want to do is just subtract to figure out how many that is, because you're not going to count on your fingers 10 through 99. So you go 99 minus 10, which is 89. But you're not just finding the difference between them. The numbers 10 through 99 could be used. So really you're technically going 99 minus 10 plus 1, because 99 itself is actually included. So 99 minus 10 is 89, plus 1 is 90. So your bottom number is 90, okay? Of course, you needed that on the previous problem as well. But multiples of 5s. Again, included within the range of 10 to 99, that includes 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95. Now, if you counted that on your fingers or whatever as we did, that's 18. 18 that were multiples of 5. But here's how you can really know whether you did this right. If I were to simplify 18 over 90, that's 1 out of 5. Now, that should make sense, because if you're doing a multiple of 5 with just a group of numbers like this, 1 out of every 5 is going to be a multiple of 5. So I think that makes sense if you really think about it. So that was number 3. Of course, number 5 we discussed. I want to do number 7 and 9 with you. So let's look at number 7. This one is probably the hardest one on here. It says 3 coins are tossed. Find the probability that 2 land on heads. So what I want you guys to picture or imagine is you just throw these 3 coins up in the air, and they all land at the same time. And you have to decide what was the probability that 2 of those tosses are actually going to land on heads. So that would allow for 1 of them to land on tails, 2 of them to land on heads. So here's how you do this problem, and this one was pretty challenging. If you think about it, your first toss, if you see those coins land on the ground from left to right, your first coin could be heads, but your first coin could also be tails, right? Those are your 2 options. Now, from here, here's your possibilities with 3 coins. You could have heads, heads, heads. You could keep that first one again, and you could keep this second one but make the third one tails. But also, if the first one was heads, you had 2 options for your second one to be heads. The other 2 options are for both of them to be tails. Well, that's where one of them would be heads and one of them would be tails. So that's it. You have 4 possibilities. If you just randomly throw up 3 coins, you have 4 different possibilities where the first one that you would look at maybe from left to right would be heads. And that's if the second one was heads, third one was heads, and then heads, heads, tails, heads, tails, heads, or heads, tails, tails. That's your only options. Now, what if you randomly threw those coins up and the first one was tails? Well, you're still going to have 4 options, because it works the same way that it would if that first one was heads, the first one's tails. You could have tails, heads, heads. You could have tails, heads, tails. You could have tails, tails, heads. Or you could have tails, tails, tails. That's really it. That's their only possibilities. So what's my bottom number here? Well, my bottom number is 8. That's my total number of outcomes. because those are my groups. These are how those 3 coins could land. That's it. There's 8 possibilities. So what's the question say? Well, what's the probability that 2 of them will land on heads? Well, not the first one, because those are all 3. How about these? That's 2 landing on heads. This one is 2 landing on heads. The fourth one is 2 tails. This one is 2 landing on heads. This next one is 2 tails. The third one here is 2 tails. And the last one is all tails. So the only possibility of throwing 3 coins up and 2 of those landing on heads is 3 out of 8, which cannot be reduced. This is my answer. So that's how you do number 7. It was kind of tricky, probably the hardest one on the homework. Here's number 9. I'd like to do it too. This one's not as hard as that one. This actually includes something that we're going to talk about soon. It's called conditional probability. But if you look at the way this one is written, it says, what's the probability of drawing a 9 or a diamond from a standard deck of cards? So remember, you have 52 cards in a standard deck. So if I am going to take 2 events, I multiply. But this is not 2 events. This is 1 event. You're drawing 1 card. You're wanting to know what's the probability that that 1 card you draw is a 9 or a diamond. So here's why this one's tricky. Because what's the probability of me drawing a 9? How many 9s are there? Well, remember I told you yesterday there's 4 suits. And each of those suits have 1 9. So there's 4 out of 52 chances, right? But then it says, well, what about drawing a diamond? Well, we said there were 13 diamonds. But here's the trick to this problem that we're going to talk about soon. There are 13 diamonds. I don't fight that. But remember, the first one was drawing a 9. Wasn't there one that was a 9 of diamonds? So technically, that one's kind of already been used up. And we're going to talk about this better later. But instead of having 13 more diamonds we could choose from, we really only have 12 because one of those diamonds got taken up as a 9. Okay, so this is something that we're going to discuss soon, but because of that, it made the problem a little tricky. So our answer was 16 out of 52, and 16 out of 52 will reduce. It reduces down, I can't remember, let me find, I don't have my calculator, oops. I don't have my calculator nearby either. But 16 out of 52 reduces down to, dang it. It's almost worth doing it again. 4 out of 13. 4 out of 13. So there's number 9. Okay. So a little tricky. We'll talk about it soon. From a kind of a more, there's a more professional way to do that problem, and we'll talk about that soon. Here's number 11. This one wasn't too hard, because we had that one in the notes. Not getting doubles. Remember, this is what we called the complement of getting doubles. Well, there's only 6 possibilities out of 36 of getting doubles. So 1 minus 6 over 36 gave me that 30 over 36, which reduces. Number 13 was easy. Number 15 was easy. So I'm going to leave those up. If you have a question about them, mark them, and you can ask me later. But those were pretty simple. If you tried this homework assignment, you probably didn't have any trouble. 17 and 19, of course, were the key word was that those were being replaced, right? They're replaced. They're independent. What you do the first time does not affect what you do the second time. However, so there's your 2 answers there for 17 and 19. However, with 21 and 23, it uses the concept of not being replaced. Not being replaced. So it's like you pull it out of the bag, you set it off to the side. So it's dependent. It affects what you do the next time. So that's why our values change. So that's number 21, 23. Those are pretty easy. Check those real quick. If you have a question, mark them, and we'll go over them. And then number 25, let me do that one. It's not that this one was hard. I just wanted to finish up here. It says all this information, which is going to be important because I need to know what my total is. So 5 plus 8 is 13. 13 plus 11 is 24. 24 plus 16 is 40. So my big number here is 40. My bottom number is 40. Let's see what the question asked. What is the probability that both players will be seniors? Okay, so the first player chosen is senior. That's 16 out of 40. Now think about this. Is this independent or dependent? If I'm choosing two players, can I choose the same two players? No. Well, if I can't choose the same two players, that means one affects the other. So there will no longer be 40 players to choose from. There will only be 39. But not only will there only be 39, there will only be how many seniors? 15. So it's actually 16 over 40 times 15 over 39. So if you use your graphing calculator, it will reduce that down for you to 2 out of 13. There's a 2 out of 13 chance. And that's it, guys. That is theoretical probability. Pretty straightforward. Hopefully you guys did really well on those. Again, like I said earlier, if you would like to go ahead and write down the ones that maybe you were confused about, and you can ask me about those at a later date, I'd be more than happy to go over them. All right? Okay, so if you don't have the note sheet for today, that's going to go ahead and get distributed at this time. If you already have it, then that's great. We're going to jump right in here in just a second. Today, we're talking about the other one that I referred to yesterday called experimental probability. Now, I'll apologize right off the bat that y'all's doesn't have color on it. Obviously, color makes it a lot better. But again, we don't have that nice of printers, so you got a black and white. Couple things that I want to talk about. I told you guys about experimental probability, or it's also called empirical probability. We talked about that the other day when I told you about flipping a coin. Remember, we said theoretical probability, it's really basic because it's like, in theory, if I were flipping a coin, what's the probability of getting a heads? Well, that's 1 out of 2 possibilities. That's theoretical. Experimental, or what we call empirical probability, there has to be data or an experiment done in order to find this probability. So that is what we're talking about today. We're going to have to rely on an experiment or on data that's already been determined or found by someone. If we are doing that, this is called empirical or experimental probability. So empirical or experimental probability. Okay? So experimental probability, and this is also a fraction, okay? We're dividing. You're going to have the number of desirable outcomes and that's going to be divided by the total number of outcomes. So really, it's not a difference as far as our ratio goes and how we're going to find our answers. The difference is, instead of just thinking through the values that we're discussing, we're actually going to be looking at data. So for example, you notice how this says the bar graph shows the results of 100 tosses? Right off the bat, what are they telling me? They're telling me an experiment was done for this dice that's right here to the right. And it's saying, hey, this dice was rolled 100 times. And every time they accumulated how many different times 1 was rolled, how many different times 2 was rolled, so on and so forth. So we are using data. This is experimental probability. Now, what I like to do right off the bat is I like to actually find specifically what these values are, so I don't have to worry about finding them later. Look at your table. If you look at this red graph, what does it look like it's at? I mean, it's between 15 and 20. It looks a little closer to 15 than it does 20, but it's not also just above the line. So I'm going to say that one's 17. Now 2, it's just above the line of 20, so I'm going to say that's 21. Number 3 is just above the line of 15, so I'm going to call that 16. Number 4 is just above the line of 10, so I'm going to call that 11. The purple one looks a little higher up, so I don't know, that's a tricky one. I think this one, I think the number 6 is a little easier to tell. To me, it looks like it's a little bit further than a half. It looks like it's a little further than halfway up. Ah, man, that's tough. We're going to say that one's 13. So do the math with me real quick. Take 100 and subtract all the ones that we've definitely come up with. We got 100 minus 17 minus 21 minus 16 minus 11 minus 13. So we're going to say that this one that I'm not 100% sure about, we're going to say it's 22. Okay? We're going to say it's 22. Now, again, maybe y'all see that a little bit differently than me, but I just feel like the yellow one looks a little above the line further than the 17 did. But anyways, that's what we're going to go with. So let's answer some of these questions. Based on this experiment, okay, based on data that's already been gathered, what was the probability of rolling a 3? Well, that's 16 over 100, right? Because that was my total number tested. Now, again, use your calculator to simplify this. Alpha y equals number 1. Plug it in, and that's going to break down to 4 out of 25. Okay? That's how easy it is. Now, how about rolling a perfect square? Now, again, remember, in this case, our bottom number is still our total, right? 100. This thing was tested 100 times. But what of those numbers are classified as perfect squares? Well, hopefully you guys remember, it's what you get when you multiply a number by itself. So if I take 1 times 1, isn't that 1? So 1's a perfect square. What else is a perfect square up here? 4. I hope that you just said that. 2 times 2. So there's 17 1's. There's 11 4's. So 17 plus 11 is 28. So 28 out of 100 of these are perfect squares. Now this reduces to 7 out of 25. Okay, next one. Rolling a number other than 5. Other than 5. Now, hopefully you guys remember this. This is still complement, right? Remember complement that we talked about with theoretical probability? You're subtracting what it's not from 1. So to find what rolling a number other than 5, it's easier to just subtract how many 5s there are. Well, there's 22 out of 100, right? So if I want to find the ones that are not 5, I'm going to subtract 22 out of 100 from 1. And of course, that's going to be 78 out of 100. And 78 out of 100, let me type this in real quick. For some reason, I have this one done. 78 over 100 will reduce down to 39 over 50. 39 over 50. All right, so there you have it. Really easy. Of course, I'll quickly do the even. Remember, your bottom number is still 100. My even numbers are 2, 4, and 6. So that's 21 plus 11. That's 32. 32 plus 13 is 45. So that's 45 out of 100. And 45 out of 100 reduces down to 9 out of 20. 9 out of 20. So there you have it. Pretty easy, right? I mean, it's just probability, but with data. You're not just having to think through the cube, which is 1 through 6. You're actually using data that's been found by someone and of course, subtracting it or adding it, okay? So here we go. The addition rule for probability is the next thing we're talking about. And there's a couple of different possibilities that we're talking about. Now, we kind of dealt with this in the homework assignment a minute ago. I thought I told you it was in conditional probability, but it's right here. If we're talking about a mutually exclusive event, that means there is absolutely no overlap whatsoever. They are completely separate possibilities. But when we talk about inclusive, that's a little bit different. And we had one of those on the homework assignment the other night, last night, that I just referred to a couple minutes ago when we were going over it. But an inclusive event is where there is overlap, okay? They depend on each other. I don't know if y'all know which one I'm talking about, so let me remind you. Y'all remember the problem that I just went over about the question that asked about a deck of cards being a 9, if you drew a card and you got a 9 or a diamond, that is this idea of inclusive, okay? So when we have inclusive events, you're going to have to actually make an adjustment after you do your probability for each event happening. So if they're mutually exclusive, I'm going to simply take the probability of A and I'm going to add the probability of B. Okay, very simple. So we have one event occurring. You want to find out what's the probability of this or that, and they don't overlap. You're going to find the probability of A, and then you're going to add the probability of B. But if it's inclusive, that's a little different, because you're going to find the probability of A, and you're going to add the probability of B. But to do this correctly, at the end, you have to subtract the probability of B given A. Okay? So let me make sure you understand this. Let's go to the back and look at number 5. It says each student casts one vote for senior class president. Of the students, 25% voted for Hunt, 20% voted for Klein, and 55% voted for Vila. A student from the senior class is selected at random. What is the probability that a student voted for Klein or for Vila? Now think about this. Are these two events mutually exclusive or are they inclusive? Well, they're definitely mutually exclusive. No one can vote for Klein and vote for Vila. You're only allowed to make one vote. There's no overlap possible between these two events occurring. So what I'm going to do is I'm going to take the probability of someone voting for Klein. Now you could do that one of two ways. You could say 20%, or you could do 20 out of 100, because that's how percents work. Plus, remember they're mutually exclusive. What was the probability they voted for Vila? Well, that's 55%, or 55 out of 100. So my possibility, if I did it in percentage, will be 75%. There's a 75% chance that I voted for one of those two. But if I change those to fractions, of course, you're going to get 75 over 100, which is going to break down to 3 out of 4. There's a 3 out of 4 chance. I will allow either one of those, but that's how you do this, being a mutually exclusive event. But look at the very next problem. This is kind of like the one we talked about just a second ago. It says a card is drawn from a standard deck of 52. Find the probability of drawing a red card or a face card. You see, I'm not drawing two cards. I'm drawing a card. So I'm adding probability here. So what's the probability of drawing a red card? Well, we talked about that yesterday. There are 26 red cards, right? Plus, my next probability is, what's the probability of drawing a face card? Well, there's a jack, there's a queen, and a king. Those are my face cards, okay? Ace doesn't count. I know a lot of people struggle with that, but ace does not count. So my face cards are jack, queens, and kings. Well, remember, how many suits have a jack, queen, and king? All 4 of them. So there are 4 times 3. There are 12 face cards out of 52. Now, does anybody see the problem with this? Am I allowed just to add these two together and come up with probability? Absolutely not. And I hope that you know why. Here's why. Were there face cards that we had already added that were hearts and diamonds? Yes, remember, hearts and diamonds have face cards. So we added the jack, queen, and king when we added the hearts and the diamonds. So we added jack, queen, and king of both hearts and diamonds. So we added those twice. So what you have to do in an inclusive event like that is subtract the overlap. We got to subtract 6 because there was a jack, queen, and king of hearts, and there was a jack, queen, and king of diamonds, and they got double counted. We're not allowed to double count. So this is an example of an inclusive event. So we had to subtract the overlap. So we're going to type all that into your calculator, and it's going to tally it all up, and it's going to tell you you had an 8 out of 13 chance of that happening. Okay? Now we're going to skip number 7. Let's look at number 8. A bag contains 25 marbles, 10 black, 13 red, and 2 blue. A marble is chosen from the bag at random. What's the probability of getting a red or a blue? Guys, is this mutually exclusive or is this inclusive? Is there any chance there's overlap here? No. You don't have a red and a blue and a red and blue. That doesn't, there's no overlap there. So my probabilities are simply, how many red ones are there? There's 13. Out of how many total marbles? 25. Plus, how many blue ones are there? There are 2 out of 25. There's no overlap. So if we add these, that becomes 15 over 25, which actually reduces down to 3 over 5 if you use your calculator. So the difference between mutually exclusive versus inclusive, okay? Okay, now let's go to the bottom, and I'm going to show you something that's a little bit harder to understand. And when this happens, it's really good to actually kind of make a chart, okay? So here's what we're looking at here. We've got 5 years after 650 high school seniors graduated. So what do you think that's going to be? That's my bottom number, right? 650. That's the total high school seniors who graduated. 400 had a college degree, and 310 were married. Half the students with a college degree were married. Okay, so let's try to decipher some stuff. Let's fill in these blanks here. How many actually had a college degree? 400. Now listen, if there were 650 people and 400 ended up with a college degree, how many had no college degree? Remember, that's the complement thing. You're going to subtract. So that's going to be your total 650 minus 400. So there's 250 who have no college degree, right? Okay, what about married? How many were married? It says 310 were married. Well, if 310 were married, out of the 650, how many were not married? Well, that's 650 minus 310. 340 were not married. And then it says, how many were college degree and married? Well, look, half of the students with a college degree were married. Well, think about that. There were 400 with a college degree. Half of those were married. So that's 200. Now, how many had a college degree? 400. So 200 had a college degree and were married. So 200 had a college degree and were not married. Now, how many were totally married? 310. How many were college degree married? 200. So how many were no college degree and married? Well, that's 310 minus 200. That's 110. But if there were 250 with no college degree and 110 of those were married, that's 140 who had no college degree and were not married. So there's a ton of possibilities here, right? So it's kind of getting crazy. But I would recommend, if you've got difficult questions, sometimes it's good to break all these numbers down, make sure you have them all correct, and then go and answer your group of problems. So look at number 10. It says, what's the probability that a student has a college degree or is married? So you're picking one person out of all this group. So here's what we're dealing with. We're dealing with the probability that the student has a college degree. Or, so plus, the probability that they're married. But here's my question. Were there any who had a college degree and were married? Yeah. So we have to subtract those that had a college degree given that they were married. So, how many had a college degree? Well, that's 400 out of 650. Plus, how many were married? Well, that's 310 out of 650. But remember, how many just got double counted? How many have a college degree and are married? Well, that's 200. 200 kids got double counted, so we have to make up with that by subtracting them. So if you go type all this in your calculator and you let it do its little thing, it's going to tell you 51 out of 65 chance of finding someone who either had a college degree or was married. This is the idea of inclusive. You add your probability, but you subtract your overlap. So look at number 11. What's the probability that a student has a college degree or is not married? So here's what we're doing, guys. We're finding the probability of a college degree plus the probability of not married, and then we're going to subtract the probability of people who have a college degree and are not married. Y'all understand that? That's the idea of inclusive. So first, how many have a college degree? 400. Plus, how many were not married? 340 out of 650. And how many were college degree and not married? Well, that was 200. So that was the overlap. That has to get subtracted back out. It got added in there twice. You can't add stuff twice. You have to make up for it by subtracting it. So 54 over 65 is what this reduces to. Okay, last one. What's the probability that a student does not have a college degree and is not married? So look, guys, this is the probability of not college degree plus the probability of married minus the probability of not college degree and married. That's what I'm doing. So what is the probability of not college degree? Well, that was 250 of those, right? So your chart up there. Plus, how many were married again? Well, that's 310. So who got double counted? The people who were not college degree and married. That's 110 if you look at your numbers. So there we have it. So it's 250 over 650 plus 310 over 650 minus the 110 who got double counted. When you type that in and reduce, it gives you 9 out of 13. So this is the concept of inclusive from experimental probability. And while we say experimental, this really wasn't an experiment. This was looking at a group of people who graduated from high school, 650 of them. So this is more of like the empirical side of it. It's numbers that had been collected. It's data. And we're basing our probability on the data. Okay? So that's how you do this. It's pretty easy, but it's also challenging. So I can kind of see both sides of it. Now, your homework tonight is going to be numbers 1 through 10. 1 through 10. So you're going to have to really look at number 7. That's going to be the one that you have to do your own chart on. So again, good luck with this. The front side only is your homework. 1 through 10 due on Friday. So if you're here today, remember you're not supposed to be here tomorrow unless you're a sophomore or senior. If you're, well, what I say today, when you watch this video, we'll decide that. But anyways, some of you will have seen this video on Wednesday. Some will see it on Thursday. This is due Friday or tomorrow. All right? So I hope that you guys have a wonderful day, and I will see you soon.